Okay. Good. All systems go. So, hello everyone. Welcome back to Big Data. So today we'll try to finish up what we started last week when we were discussing the basics of NoSQL, distributed NoSQL data stores. And if all goes as planned, we will also cover Big Table on HBase this week. Before anyone asks, there is no quiz this week because there was no new pre-session reading material. Next week, we will move on to discuss decentralized NoSQL data stores and look into DynamoDB and Cassandra. There will be new pre-session reading material next week and a new quiz next week, and that will be the last quiz for the semester in the course. Okay, cool. So this is where we stopped last week. We were discussing how we can achieve high write throughput and possibly low read latency in the setting that we were targeting. And we went over a number of ideas. You may remember how we had these group discussions. We were discussing how data should be partitioned and so on. So we will revisit all of those discussions today. Okay. Starting with this guy here, the log structured merge tree. So we were saying last week that random IO should be avoided as much as we can. Now there is evidence, as in papers, academic papers published in peer-reviewed venues, that show that if you have a fast enough disk, like an SSD, sequential IO on SSD can even be faster than random IO in RAM. So random IO, if we can avoid it, we should avoid it. And we said that one way of avoiding random IO when we write stuff is to, well, never do it. You always try to append to your data. So essentially what you have is a log. You have this file or this concept of a file to which you always add data to the end, you append. And this data is appropriately tagged, might have a timestamp, might have a version number, something along those lines, so that you can discern which version of a data item is newer or not. And sure, I mean, appending stuff to a file is okay, but then how do you find anything in this big file? And this is where the log structured merge tree comes into view. Now, the LSM tree is a general data structure. Here, for the purposes of this course, we only see a simple version of it. So we look at a log structured merge tree that only has two levels. We call them L0 and L1. L0 lives up completely in memory. So every time you try to write something to this file, let's say to this storage, you have this buffer in memory to which you always append data, right? So you append data, append, and at some point, this buffer you have in RAM will fill up. Okay, so that's your level 0, this buffer in RAM. You might have multiple buffers. For example, if you have multiple, let's say, tables that you append to, or multiple files that you want to create, you might have one of these buffers for every file or for every table. But I mean, this collection of these buffers is your level 0. Every time one of these buffers fills up, what you do is you take the buffer, you sort it by some predefined ordering. Typically, you sort it first by key of the item, then by column name, and we'll see what these are, then by timestamp, and then that's what you store. Okay, so every time this buffer fills up, you create a new small file on disk, and this file is immutable. We can call this a spill file. As we'll see shortly, HBase call these H files. Bigtable calls these SS tables, and I think SS table is also the canonical name used by the LSMG, if I remember correctly. So now this collection of these immutable files is your L1. This is the second level of the tree. Whenever you need to update a value, that let's say you insert a value at some point, and then in the future you want to update it. What you do is you go and append a new version for that value to this log. So you append it in main memory. When that thing in main memory fills up, you write it to disk, and on you go. Okay. Same for deletes. You never go back and delete something in place. What you do is you append a so-called tombstone record, or a deletion record. It's a record that says that something with this key and maybe these other characteristics that was inserted in the past is now no more. Okay. Now there's a couple of downsides to what I just described. One is, and I wonder why no one has asked this so far. Maybe you've read the LSM material. The first problem is that, as I said, I append things to this buffer in memory, and when the buffer fills, I write it to disk. So what happens with the durability in between these two time points? So if I have stuff in my RAM and the buffer is not full yet, and the server that holds this data goes down, what happens to that data? Do I lose it? And the answer is I would, unless I took some extra steps. And the extra steps in this case is yet another log, what we call a write-ahead log. So this is a log of operations to which you append, you log what mutations were done to your files. And one trick we play, I mean, so this is sort of counterintuitive. We're doing this whole thing of writing things in RAM, fill up the buffer, then write it to disk to alleviate touching the disk as much as we can. And now we go and introduce a log for these operations. What gives? So what gives is that this log is not synced to the disk for every single operation that we do. What we do instead is the trick that the database world calls group commit. So we group together some of these mutations, some of these log records that would be written to the log. And every now and then, maybe every that many log records or every that many milliseconds, we flash them to disk. Okay. And a write, so I'm a client, I send an insertion, a write to this data store. This write is acknowledged to the client. So the client sees this write as being completed only after the data has been written to the log, but not necessarily waiting for the data to be, for the buffer to fill up and the data to go to disk. Does that make sense? We have practically two versions of this data, something that's in this write-ahead log and something that is in our LSM tree. Okay. And by grouping these mutations together and by grouping these log records together and only flashing every now and then, essentially we amortize the disk cost. Still, the problem is not completely solved. So if something bad happens in between two flashes of the write-ahead log, then that data will be conceptually lost. But since we haven't acknowledged the write back to the client will see it as a failed write and then will retry the write. Okay, so the data is not stored on the server or the cloud side, but the client also doesn't consider the data stored. So the client will then retry the write. So all will be good eventually. Okay, that was the first problem. The second problem with LSM3 so far is that every time we do an insertion, it seems like so far that the size of the store increases because we add something to this in-memory buffer, we spill the buffer to disk, and eventually we have more and more and more of these buffers. Okay, but the same thing also happens. I mean, that's something that we would expect for insertions. But then when we do updates will also lead to an increase in the size. Deletions will also lead to an increase in the size because remember, a deletion is just an insertion or an append of a tombstone record. Okay, so this doesn't sound good. And the trick that LSM trees play is that of compaction. So every now and then, and the every now and then can be defined on the basis of either time or space, or there is a third option here that we won't really cover. I'll just mention it. So the LSM trees that were defined and used in the Bigtable and the HBase papers, they were doing compaction either based on time or size. So when my level one has reached a certain size, I will do a compaction. Or after that long, I mean, since my last compaction, I will do a compaction. Okay. The problem with this is that, I mean, what does compaction do? Let's get this out of the way. The compaction will go through all of these spill files I have in level one and will pretty much mash them together. Remember, these spill files are sorted by key, so it's easy to merge them because it's like a merge sort. I mean, like the same trick we saw when we were discussing what happens with the output of mappers and the output of reducers like 2-3 weeks ago, probably more than that. So in doing so, in merging these files, whenever this compaction algorithm finds, let's say, an update record, what it will do is it will retain the new version of the record and throw away the old version. Whenever it finds a tombstone record, it will throw away the tombstone record and also throw away whatever existed for that record up to that point. Okay, so essentially, compaction applies these in-place updates, but it does so in a lazy manner. So, you know, when my size reaches a certain point or whatever, and it does so by scanning through these spill files. So again, there is no random access IO. There's no random IO, right? It's all just scan still. Now, this, as I said, was the original implementation. So I'll get to the third criterion, actually, not necessarily criterion, but I'd say probably technique. So the third option, I mean, what's the problem with the first two options? The problem is that this size, the size you have in level one, could grow if you go by time. Then the size of L1 could grow very, very big, very large. And then you have a lot of data to compact. And then compaction can take too long. I think there was anecdotal evidence of systems in one or more of the big players where the compactions were taking so long that before a compaction ended, it was the time to start a new compaction. Okay. With size-based compaction, again, you find yourself in a situation like this. You need to fine-tune what is the size at which you will do the compaction. And you know, people used to err on the side of let's say, caution. So they were not, they wouldn't configure their systems to run compactions quite often because the compaction, it does take up resources. The third way of doing this is what is now called the level-based compaction, or the level-based log structured merge trees. You may have heard of a system called LevelDB. I think LevelDB was the first one that actually used this level-based compaction. Don't quote me on that. If I remember correctly, LevelDB was the first system to actually use it. And it's what most systems use these days. RocksDB, for example, which is also an LSM, and it's used as the storage substrate from a number of commercial databases, is actually an LSM tree that's using level-based compaction. Well, in level-based compaction, what you do is you predefine the size of what you could call a segment, right? So you say that, what's the size of my buffer in RAM? That much. I will have spill files in level 1 that are that big, and then I'll have a level 2 and level 3 and level 4 and so on that have segments or spill files that are exactly that big. And what happens is level 0 works just as in the old school LSMs. You just append stuff, you add stuff to this in-memory buffer. When the in-memory buffer fills up, you sort it, you store it on this. And now you have your level 1 segments, okay? What happens then is that when the number of segments in level 1 reaches a threshold, let's say 10, you then merge them into level 2 segments. And you do this so that the following holds. So in level 1, the segments you have, they are sorted, but they might have overlapping keys. So there might be a key for which you have a value in one segment and in another segment, in another segment. In level 2 and onwards, that doesn't hold. So in level 2 and onwards, every segment only has, actually every key can only appear in one segment or its subsequents, right? So in level 2 and below, the segments actually partition the key space. And what this means is that when you try to do this merge, you can know beforehand which of these segments you will need to touch, okay? And the extra thing that you gain is that when you're looking for the data, when you look for data, you only need to look at only a specific subset of those segments in the lower levels. Okay, so it's faster to do the compaction, it's faster to search it. It's a generally better design, but we don't really cover it in this course to alleviate the extra complexity. I mean, you already have enough things to understand and remember. Okay, so with these things in place, so the in-memory buffer, that's the level 0 of the LSM, the write-ahead log, the level 1, which is the spill files, the compaction, we've got the basic skeleton of an LSM, okay? And so far, what we've managed to do is avoid random IO at any point during the write protocol, okay? Nothing in the write is a random IO. Well, apart from sorting the in-memory buffer before you write it to disk, but still, you can, anyway, right? So I think that's the one random IO we cannot alleviate, and that is just in memory and just for the small buffer, so no big deal. But what happens with reads, right? So we still need to go through many spill files. Whenever we need to read a data item. So a read request comes for a key X. Where is this key X? Where does it live? We have all of these spill files, so we need to potentially scan through all of them to find all the versions of X or all the pieces of X, because sometimes what happens is if we have a database record, let's say, that has a key and many columns, it could be the case that these columns have been inserted at different points in time, and hence they appear in different spill files. So if the client requests a read for the whole record, for the whole row, we need to go through those spill files and assemble the response. So we need to solve this problem somehow, right? So we need to find a way of isolating only those spill files that have the data we're looking for. And then even within those spill files, have a way of quickly getting to the data or seeking to the data we're looking for. Okay, so these are the two problems we need to solve. Before we move on, there is a question here. It says, to remove tombstone records, won't you need to scan the entire set of files? Yes, so when you do this compaction, essentially, you are scanning all of the files you have on disk. You can do compaction in like we did with the mappers and reducer stuff in MapReduce. So you can take spill files in pairs, merge them in pairs, and then merge the output of that in pairs, and so on. Essentially, at the end of the day, you are scanning the whole thing. Yeah, indeed, you need to scan the entire set of files. And someone asks for pictures. I don't have a picture, I'm sorry. What I could do is I could go and add the picture when I upload. When I can update the version that's on Moodle and add the picture, or even post the picture on the Moodle forum. I think that one of the extra reading material for the LSM did have pictures, right? Isn't that random IO then scanning for tombstones? No. So think of it like this. You have your spill files, right? You get a pointer to the beginning of every spill file. And these are sorted by key, okay? And what you do then is essentially you move along them, merging what you see. So you look at all your pointers and see which one has the lowest key, the smallest key, okay? That key is now added to a new spill file, right? It's appended to the beginning of a spill file. And then you move that pointer to the next record in that one spill file. And now you check all your pointers again. Which one has the smallest key? That is the next thing to be added, right? So just like sort merge, like merge sort. Yeah. Now, while you're doing this, at some point, you might get to a place where the same key appears in many spill files. And some of those spill files, they will have a record for that key, that the record would be an insertion or an update, again, like an insertion, or a tombstone record. And when you find the tombstone record, you need to, that's essentially a signal to ignore all other insertions that predated this tombstone record, but not insertions that succeeded this tombstone record. Okay, so you're not doing random IO. You're scanning through those spill files and you're appending to your result. Okay, no random IO in this process. Okay. So let's try and solve these two problems we just said. So the first problem is we need to find a way to say that a spill file contains or not a key that we're looking for, without actually reading the spill file, of course, right? So the way this is done in most of the existing systems is by using a statistical data structure called the Bloom filter. Now, You may have seen the Bloom filters again in the past. I'll just do a quick recap of what Bloom filters are. So essentially, it's a representation, a statistical or probabilistic, I should say, probabilistic representation of a set. Okay. It offers the following three basic ops. So you can insert an element, you can remove an element, and you can check whether an element is in the set. And as a matter of fact, the removal is not supported by all types of Bloom filters. There's many types of Bloom filters. They have been around for decades, so people have twisted and turned them in different ways to suit their needs. So let's see a little bit about how this works, right? So let's say you have a set S, and this set has n items. Okay. Let's suppose for now that these items are unique. Each one of these items is unique, but not necessarily, they do not cover the whole domain of whatever S is. Okay, so if I have, the domain of, let's say, all users in a system, and I want to, I have a file that only has 1,000 of those, then the size of the set for me is 1,000. It's not the domain of all users. Okay. So this saying is how many items I want to have in my set, not how many items I could potentially have if I had all the possible values in this set. Okay. And now this set is represented by a bitmap, let's call it B, of size M. Okay. Typically, n is much larger than m. Okay. We start with b initialized to all 0. So when we first instantiate the Bloom filter, all the bits are zeros. And then when we want to add an element, what happens is we take that element, we hash it. Typically, we use, or actually, I don't want to get into that. There's a specific set of families of hash functions that are good for use in a Bloom filter. They need to have specific statistical properties. We have a bunch of those off the shelf, so we just take one of those hash functions that are good for this case, right? So when we take the element we want to insert, we hash it, and then we do a modulo m, and that gives us the position, a position in this bitmap where this element maps. And then we just go and set that position to 1. Okay. Now to check if an element is in this set, we again take this element, we hash it, we take the bit position, and then we check whether the bit position is set to 1. If it is set to 1, then the answer is yes. If it's 0, that position is 0, then the answer is no. Now, you probably noticed that there could be a case where multiple elements, hashed and modulo m, map to the same position. So, and this is a bitmap. I cannot set that more than once. I mean, if I set it once, it has a value of 1. If I set it again, it has again a value of 1. Right? So when I check for membership, when I check whether something is in a set, I could find that the bit is set to 1, but that could have been set by a different element, the one I'm looking for. So this is what we call a false positive. Okay, this is a situation where I would say this element is in the set where it actually isn't. Okay. Now, fundamentally, with Bloom filters, what we do is we trade accuracy for space. So we can increase the size of the bitmap. We can increase m, and the more m increases, the lower the probability that this kind of collision will happen. So this is the typical space accuracy trade-off here. The thing is that for many applications, false positives are acceptable. So as we will see in the next couple of slides, we use these Bloom filters. We have one of these Bloom filters next to every spill file. And what we do is when we have a key that we're looking for, we check for that key in the Bloom filter. And if the Bloom filter says yes, then we will scan that spill file. Okay, if the Bloom filter says no, then we won't. Now, there is no possibility of false negative. If the Bloom filter says no, it's definitely a no, 100%. If the Bloom filter says yes and it's a false positive, what will happen? We will scan a spill file that we didn't have to scan. We're not losing any data still, right? So in this case, false positive is not the end of the world. And we will see how we can tweak the Bloom filter to reduce the number of false positives. Okay. So the trick that we will play then is a very, let's say, popular or standard trick in these probabilistic data structures, and that is the trick of statistical averaging. So instead of setting only one bit for every insertion, we will set multiple. So we will have more than one hash function. And every time we insert something, we will compute the output of all of those hash functions and set all of those bits to 1. And then when we want to check for whether something is in the set, again, we will use all of those hash functions and we will check all of those bit positions. And if even one of those bit positions is 0, then the element is not in the set. Okay. So the parameters we have are, these are wrong. So the bitmap size m, sorry, not n, versus the set size n, sorry, not capital N. And then we have the number of hash functions, and this should be k. So apologies, these symbols are from a, I updated the symbols last week, forgot to update this slide. Okay, I'll update this and upload again to Moodle. So just to avoid any confusion, m is the size of the bitmap, n is the size of the set, kappa or k is the number of hash functions. So let's see what happens with false positives. So what is the probability that the bit is set is 0 after adding one element and using just one hash function? With one hash function and one element inserted, only one bit will be set. Okay. So the probability that any bit is set is 1 over m, because I have m bits. And the probability that any bit is 0 is then 1 minus 1 over m. Okay. If I use k hash functions, then the probability that any bit is still 0 after an insertion is whatever I had previously to the k, because with k hash functions, I've now set k bits. I've done this process k times. Now, if I add n elements, sorry, not s, if I add n elements using k hash functions, this is then again raised to a power of n, and then the probability becomes this. Okay, 1 over m being the probability that any bit is set, 1 minus 1 over m the probability that any bit is unset, to the k for k hash functions, to the n for n elements. Okay. And now the probability that any bit is set after adding s elements with k hash functions is 1 minus this. Okay. So what's the probability of a false positive then? It's the probability of a bit being set and us looking at that bit and seeing that it's set. So since we're using k hash functions, we have k bits. We take the probability we had previously, and that is a probability that any bit is 0. 1 minus that gives us the probability that any bit is set. To the power of k is that all k bit locations that I will look are set. Okay, and that gives us, this is a good approximation of this expression. 1 minus what do you call this? Sorry, I'm looking. E to the minus km over m, and all of this to the k. Okay. Now, again, if you are really into statistics and so on, this is not exactly correct. There have been a couple of papers that prove that this is not correct. We don't care. It's not the subject of this course. Okay. And then, given this, we can derive equations to compute the optimal number of hash functions and the optimal number of bits given the number of items in the set and a target false positive probability. And I have an example here. If, for example, I had a set with 1,000 items, and I wanted to have a false positive probability of like 5%, then the optimal number of hash functions is 5, and the optimal number of bits is 6,000 something, or 778 bytes. Okay. Anyway, so that was a fairly big detour, but understanding Bloom filters is, I mean, at least understanding Bloom filters at a high level is fairly important. Okay, it's one of those data structures that you might bump into times and again. They've been around for ages. Originally, they were created for web caches, for proxy servers for the web. But they've found applications in many other situations. Okay, so with that said, then I mean, this moves on to Bigtable and HBase. Just to assemble the picture, the big picture. We've seen how we can write to this LSM tree, and we have no random IO. Now, when we try to read stuff from the LSM tree, what we do is we have a small Bloom filter attached to each spill file, and we can check these Bloom filters fairly easily. We can actually, even have them in memory if we have enough memory. These are small structures, so you could have, a few bytes attached to a spill file that is several megabytes large. Okay, so we check these Bloom filters, and whenever one of these Bloom filters gives us a positive result for set membership, we will go and scan it. Now, we don't scan the whole thing. What happens is the next step to this, and the next step, we will see it again for HBase. I'll just give you a forward reference now, right? The next step is that since the data in the spill file are sorted by key, what I have at the beginning or the end of the spill file is typically at the end is a block index. So I have a little table that has taken this big file of mine, this spill file, has broken it down into blocks, conceptual blocks or actual blocks, and has a mapping that says, what is the key I have? What's the first key I have at the beginning of every block? So then this is like an index, this little thing I just said. That's why we call it a block index after all. So you can read that small index from the end of the spill file, and then seek in the spill file exactly to the point where your data item might appear. Okay, it's not a complete inverted index, it's not a complete secondary index. It's like the clustered indices we had seen in the databases, right? You can seek to several to different places within this file, and you know what is the range of keys in between those places, but not necessarily what are the keys that do appear in there. Okay. And this addresses the second problem we said earlier. So now we have a way of only scanning the relevant or relevant with high probability spill files. And within those spill files, we don't need to scan the whole thing. We can use the block index to only scan a specific subset of the spill file. The extract step that we'll again see with HBase is that you then go and create a caching memory, what HBase and Bigtable call a block cache. So every time you go and read one of these blocks from one of these spill files, you have this caching memory where you will go and store it, and you will remove it from the cache only when the cache becomes full and the thing you're looking for, and the block is no longer hot and so on. Typical cache stuff. Okay. Now all of these together, combined, allow us to have these fairly low latency reads. Okay. So let's move on to HBase and Bigtable. What's the time? Okay, yes, let's move on. Or actually, are there any questions before we move on? Don't see anything new coming in Slido. So I'll just continue. If there's anything you don't understand about LSM trees so far, just ask on Slido and I'll come back and answer. Okay. So one of the things we discussed last week was what's the best way to partition our data? And we were considering horizontal partitioning or vertical partitioning or something in between. And of course, there are pros and cons to all of these options. What Bigtable HBase has done and what many other database systems out there have done is they've taken a hybrid approach. And I think the last thing to report on the discussion last week actually mentioned this hybrid approach. So what is a hybrid approach here? You can do you can partition your data first by row and then by column, right? First horizontally and then vertically. And what this means is that out of your big table that has multiple columns, you take a contiguous sequence of rows. So that's your horizontal partition, right? And then this horizontal partition, you chop it into smaller partitions vertically, okay? The other way of doing a hybrid is vertical first, then horizontal. So you take your data, you split it in, you take subsets of columns, and these are your vertical partitions. And now within each of these vertical partitions, you partition them in smaller partitions horizontally. So you take contiguous ranges of sequences of rows, okay? What HBase and Bigtable do is actually it's actually pretty much the first. So you partition first by a row. You take a contiguous range of rows, and that is your high-level partition. And that is actually, let's say, the unit of replication. So this range of rows is what you will replicate around the cluster if you need to create replicas. And now each of these ranges of rows is split vertically. So you say the first that many columns, and then the next that many columns, and the next that many columns. They are stored separately from each other in separate files. Okay. Within each of these files, you have a mini row store that stores all the data for the columns in your horizontal partition, in your range of rows for the columns in that partition. And then you can look at the different files if you need different columns. By the way, I should say that these horizontal cuts is what Bigtable calls a tablet and what HBase calls a region. And the vertical cuts are what I think both of them call column families. Okay. And we will see a picture of this shortly. What degree of fluency do we need with those calculations? None. There is a question on slide. I'm guessing it refers to the Bloom filter calculations. You're not expected to be able to replicate them or anything like that. Okay. They are in the slides for your information. There's sort of a detour there so that you understand how Bloom filters work. You're not expected to memorize them or anything like that. Okay. So what are the basic components of Bigtable and HBase? First, you have a master node. And the master node is pretty much the equivalent of the name node in HDFS. HBase calls this the H master, and Bigtable calls it just the master. And what the master does is it maintains pretty much a directory of what of these partitions, like tablets or regions I said earlier, is stored on which tablet server or region server. And tablet servers or region servers are the second type of component in these systems. And these are pretty much the equivalent of data nodes. Okay, these are the guys that handle the regions, and this is where the LSM is actually implemented. So each region server implements a bunch of LSM trees, one per either one per region or one per table that it serves. Okay. And then we have the client libraries that communicate with the master node to get the locations of the data, and then communicate with the tablet servers to get the actual data. And this should all be very familiar because this follows on the footsteps of HDFS and the other systems we've seen so far. And this isn't really a big surprise if you consider that these systems came out of the same place right around the same time. Okay. Now, in addition to these basic components, there's a couple more. Okay. One is the actual storage of the data. And if you haven't studied these papers, you wouldn't necessarily see this coming. The data that Bigtable and HBase manage is actually stored on HDFS. So at the lowest level, or when we were discussing the LSM tree, right? Your level 1, which is where this data is stored, is on HDFS. Level 1 is still in the memory of your tablet server or region server. That's level 0 is at the tablet server or region server. Level 1 of the LSM tree is on HDFS. But remember now that here we're talking about a region server or a tablet server. These guys might be the equivalent of the data node, but they're not a data node. So it's quite often the case that you could have a region server serving a region whose data resides on a data node that's not on the same server as the region server. And I think I have a picture of that later on. Okay, so the region server is just this implementation of the LSM. It's where the level 0 of the LSM lives. It's where the block cache we talked about earlier lives. It's not necessarily where the actual data lives. Okay, you could be doing multiple network hops to get to your data there. The other component here is Chubby or Zookeeper. Chubby for Bigtable, Zookeeper for HBase. And in case you didn't guess it, Zookeeper is the open source implementation of what was presented in a paper titled Chubby that came out of, again, the same place as Bigtable and HDFS, Google FS. Okay, so Chubby is this distributed logging service, and we'll see about it a bit more later on. The quick version of what Chubby is that it's a collection of servers, typically, 5, 7, 9, usually an odd number of these guys. And what they do is they collectively implement what is known as a replicated state machine. So they run a protocol like Paxos, or in the case of Zookeeper, I think it's called Zab, that allows them to collectively agree on a global sequence of operations. So whenever you do something on this Chubby thing, and what can you do on this Chubby thing, by the way? You can store stuff, but typically you want to store small stuff, because running these protocols to make sure that they all have the same view of the data is not cheap, right? You don't want to store a large amount of data on these guys. So what kind of data do you store? You store things like logs. So you can say, I will insert, think of this as a key value store, right? I will insert a key that says tablet server X now has a log on tablet Y. Okay, so just this mapping of X to Y and a bit that says this is a log. And all of the servers in this in this mini cluster, in this ensemble, will have that in their store. And if you have a sequence of logs and logs, all of them will have, and all of them will agree on the same sequence of logs and unlogs. Okay. So you can store this like small data on there. You can use this to implement logging, and as we will see later, you can also use this to implement other things. You can use pretty much Chubby or Zookeeper as a channel to communicate control information across your cluster in a way that is highly fault tolerant and strongly consistent. Okay. Now, what is the data model of Bigtable and HBase? Or actually, I see the time is 12 o'clock. Let's take a quick break, 5-minute break, and then we continue with HBase, okay, and Bigtable. So see you all back in 5 minutes, 12:05 my time. Okay, we're back. Let's continue. So what is the data model then that Bigtable and HBase implement? Essentially, these guys are sparse, distributed, persistent, multidimensional sorted maps. Okay, let's try and decompose this a bit. So this is a sparse map in the sense that, I mean, it is a map in the sense that it maps keys to values. It is sparse in the sense that not all keys need to be existent, and not all keys need to have the same number of attributes or columns. Okay, it's multidimensional because exactly you have rows and columns, right? For every row, you can have multiple columns. It's distributed because the data is, as we said previously, partitioned and replicated. Okay, and you have this master worker architecture. It's persistent because the data is stored on disk, and it's sorted because, well, as we said earlier, this data is sorted first by key and then potentially by some other attributes of the data, like column name, timestamp, and so on. These guys, they provide a table-like abstraction. So you can think of your data as being structured in a table where you have rows and columns, but this is not a relational database management system, right? You have no transactions. To be precise, both Bigtable and HBase support single row transactions. So if you make any mutation to a row, that mutation is atomically visible. But that's not what we would call typically a transaction in the database sense would encompass multiple rows, multiple items. There is no normalization. There's of course no relational API out of the box, and no proper schema. So you can consider your data as living in a table, but it's not a relational table by any means. What the user defines is the table name and the set of column families. And again, remember, column families are these vertical partitions. Yeah. Everything else is fair game. So what the goal was here, what the original design goal was, that to allow clients to know and exploit the physical localities of their data. So the user, as the user, can play around with things like what the row key is, what the column name is, what the timestamp is. And in playing around with these things, they can sort of force or give hints to the database to store some of these items together. And if they're stored together, then it's faster to access them at query time and so on. Okay. The data you have in this sparse distributed persistent multi-dimensional sorted map, blah, 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 you can address them by row key. And typically you always have a row key. It's required to have a row key. If you don't have a row key, you at the very least need a range of row keys. And if you don't have a range of row keys, you end up scanning the whole thing. Okay. So you have a row key. You can also address your data by row key and column name, or by row key and timestamp, or by row key, column name, and timestamp. And as you probably have guessed, the more you define when you access, the more of these constraints that you define, the finer the granularity of what you get back. So if you issue a request, a read request for just a row key, you will get back all columns and all versions of those columns for that row key. If you issue a get request, a read request for a row and a column name, you will get back all versions of that column for that row key. If you issue all three of them, you use all three of them in your read request, you will get just the one version for that one column name for that one row key. Okay. So essentially, this is a 3D map. You map from row key, column name, or let's just call this column name for now, and timestamp. Have this triplet, and you map this to a value. And if you squint a bit, this is actually a key value store, because this triplet is your key, and the value is the value. Okay. Now this here is important, because the data you have in HBase Bigtable and most of the key value based NoSQL stores is actually this collection of keys and values, where this is your key and this is your value. Okay. Now we call this key and value a cell. Okay, that's the term used in the papers. That's the term used in the relevant literature. Each of these cell values is just a byte array. So the system itself does not try to interpret in any way what you've stored in there. It doesn't know whether, for example, your row key is a number or a string, like characters, or an image or a video or anything, just about anything, right? It doesn't make any such assumptions. All the system sees is a sequence, an uninterpreted sequence of bytes. Okay, and this includes row keys. It also includes column qualifiers. And what a corollary of this is that whenever the system sorts, orders rows or things within the rows, this ordering is lexicographic. Okay. Now, if you don't remember what lexicographic ordering is, think of numbers stored as strings. So you have number 1, number 10, number 2. Okay. The numerical order would be 1, 2, 10. The lexicographic order, if you translated this into strings, the lexicographic order would be 1, 10, 2, right? Okay. If you guys don't know, if anyone doesn't know what lexicographic ordering is, please ask on Slido or on Moodle, and I'll upload the link. Okay. Now, this is something that quite often catches newcomers to these systems by surprise, because you go and insert, data in there. You expect it to be ordered in, like in increasing or decreasing order, but then you look at your data and you see these discrepancies exactly because the ordering is lexicographic. Okay. If not all of your keys have the same length, then shorter length keys will be ordered before longer length keys, and so on. Then the columns are grouped into column families. Again, these are the vertical partitionings we have. Okay, and the column name we mentioned earlier on the previous slide, the column name is actually a concatenation of two things: the column family name and a column qualifier, right? Now, if for those of you who are interested in this, and you might use HBase or whatever in the future, typically the column family name is an ASCII string, a printable ASCII string, and the qualifier can be anything. As it says up here, the column qualifier for the system is just a byte array. But this first part, the column family name, needs to be a printable ASCII string, and even more precise, it needs to be a printable ASCII string that can be part of a path. And we will see why that is the case shortly. Typically, you want to have a small number of column families, but these column families can be very wide. So You can have millions of columns in every column family. We don't want to have too many of these. Again, this will become clearer soon. And as I said, the column family name must consist of printable characters and, even more precise, of characters that can appear in a path. The reason why this is so is because data within a single column family is stored together on disk under a directory named after the column family. So if you have a table called table, and you have a column family called column family A, all of the data for that column family A would be stored, remember, on HDFS, yeah, under a directory, under a path that's the name of the table, and then the name of the column family. And in this directory, you will have all the files for this column family. Okay, so this is the reason why you want the column family name to be valid path characters. What does this mean now? It means that we've, essentially done this vertical partitioning. If you want to run a query, remember what was the whole gist of column stores? It was that if you had a query that only needed data from a specific column, you could seek in your store and only read a consecutive subset of your data, and all of the data would be for your column. Okay. Now here we have the data for a column family, which is the closest we have to the columns or to the vertical partitioning here, being stored under one directory. So if you have a query that only touches columns within this column family, you only need to read the data that is under this directory, and you can completely ignore all the data that belongs to other column families. You don't even touch the files for those column families. Okay, and just to put again everything in context, the files that are stored in here in this directory are those spill files of the LSM we were referring to earlier. Okay, so this in essence allows for, this is a design decision when you create your HBase table. It allows you to group together columns that are accessed together more frequently. Okay, so if you know, for example, that you have many queries, or your most frequent query wants to scan name and age, right? Then you would create a column family that would have name and age as its columns. So whenever you run that query, or that very frequent query, you only look at that column family's data. Okay, just an example. So this sounds like a column store so far, only with the slight deviation that you don't have one column at a time. You have a set of columns at a time, being your vertical partitioning. Now, each table cell may have multiple versions. That's why you need that timestamp in the triple that makes up the key. And the timestamp can be actual time, or it can be some user-defined quantity, some number that just increments every time you create a new version. By default, when you run a query on HBase or Bigtable, what you get is the latest version of each cell. Okay, you can instruct it to give you more versions, or all versions, or versions up to some point in time, or versions up to some number, blah, blah, blah. These are all, these need to be explicitly defined in your query. If you don't define any of these, and you just ask HBase or Bigtable to give you row X, you will get back the latest version for every cell in that row. Okay, good. Now, the thing here is that there is no such thing as a row in the traditional sense. So in a database, in a traditional database, like the ones we were discussing in IDSS or database systems, you have your record or your row, the same thing. And this record consists of, all of the values of the attributes of that row sort of concatenated together, plus metadata, of course, right? So what this means is that, essentially, that whatever is the primary key for that record, for that table, appears only once in the record alongside any other column values. Okay. Here now, instead, the row is just a concept. It's the row is defined as the set of cells of a table that share the same row key. Okay. So remember what the cell is. You have this triple that is row key, column name, timestamp, and then a value. Okay. Take together all of these cells that have the same row key. This makes up a row. Now, for these systems to be able to support queries for complete rows efficiently, they need to make sure that these cells are stored next to each other. So within each row, and within each spin file, the data is sorted by row. And then within each set of cells that is sorted by row, but within each set of cells that share the same row, the data is further sorted lexicographically by column qualifier, and then numerically by timestamp. Okay. And what happens then is that if you take the file of the column family, you will see that, think of these cells, of these quadruples, these key value pairs, being sorted in this way. What happens is that you first have all of the key value pairs, all of the cells for row key X, then all of the cells for row key, let's say X plus 1, then all of the cells for row key X plus 2, and so on. Okay, so if you want to read all the data for row X, what you do is you seek to, like, the beginning of the file or whatever, and then you read a contiguous region, you scan through that file until you find a cell that has a different row key. Okay, and then you can do whatever you want with what you've scanned. You can filter out things that are older versions or not. You can filter out cells that are not that are for a specific column or not, and so on, depending on what the query is. Okay. So the data would be stored a bit like this. So if we have row keys here, column names, and timestamps, and this is the value. So all of the cells that have a row key of 1 would be stored together. All of the cells with a row key of 2 together. All of the cells with a row key of 3 together. And then within each of these groups of cells, they would be sorted first by column name. So C1, C2, C3, lexicographically. And if we had multiple of these with the same column name, meaning these are different versions of the same, different versions for the same column, this would be sorted numerically by the timestamp. Okay. Good. Any questions so far? No? Okay. Moving on, and we'll return. So is this a row store? This looks a lot like a row store, right? So you have all of the columns, all of the data for a row being stored consecutively. Then all of the data for the other row, all of the data of the other row, right? But remember, this is what happens within a column family. So if you have a table that has 2 column families, you would have this in the first column family, and then you would have a similar grouping, but with columns of the second column family in the files in that directory of the other column family. Okay. Okay. So how do we scale this? If we want to scale anything, we've said this in the past, we need to pretty much partition and replicate. We need to partition so that we can distribute the load across many servers, and then we typically replicate to achieve a level of fault tolerance. Now here, since the data is stored on HDFS, replication is taken care of by HDFS or Google FS for Bigtable. I'll just gloss over this question because I think we discussed it to great length. Huh? Yeah. So we have this, the tables are partitioned horizontally into tablets or regions. Obviously, the horizontal partitions we said earlier. Each tablet or region contains all rows in between a start and end row key. And then each of these is then assigned to a region server or to a tablet server. And this is also the unit of distribution, the unit of load balancing, the unit of replication. Okay. So let me see. So if we have this data collection that we've seen in the past as an example, the key value representation would be like this. So let's say we have, X is the column family name. So we have two column families, X and Y. The key value representation would be like this. So first, everything for row key 1, everything for row key 2, everything for row key 3, grouped by column family name, grouped by column name, then by timestamp and so on. But keep in mind that the Y stuff would be stored in a different directory. So this is just, to visualize this concept. And now let's say we have two regions. The first region is from 1 to 2, rows 1 to rows 2. The second region is from rows 3 to whatever. Okay. So then the first region would only contain the data for rows 1 and 2, all of the data for rows 1 and 2. The second region would contain all of the rows all of the data for rows 3 and onwards. But then again, remember that this data won't be stored as such on disk, right, on HDFS. The data for the first column family would be stored in files in a column family directory for X. The data for Y would be stored in files in a separate directory for column family Y. Okay. Okay. So this is the layers of this onion. So first of all, we have this logical view of a table where we have conceptually rows of data, and these rows have attributes, columns, and some of these columns might not exist for all the rows. It doesn't matter. But the logical view is this, right? So this 2D map. Okay. Or not 2D, this multi-dimensional map, I should say. This is then split into regions horizontally. So we do these horizontal cuts here at F, here at L, and so on. And then we have these regions. But each of these regions is then mapped to a region server. Okay. And it's further split vertically at column families. Okay. And the client then connects to region servers to read the rows. As a matter of fact, the client connects to the master and the zookeeper or Chubby to find the location of whatever it's looking for, to find the region server that's serving the rows the client is looking for. And then the client will contact the region server. And there is an extra step after that, which is that the region server now needs to contact the name node and go to the data nodes that store the data for these for whatever the client does. Okay. So this is the canonical example of a use of this system of Bigtable and how this was used by Google. And this might actually some context to this discussion too. So remember, Google was doing these crawls of the web, downloading web pages, storing them somewhere, and then they wanted to go over these web pages and process them and create their inverted index. Okay. we've said in the past that HDFS was used as the sink, so the crawlers would just dump the stuff on HDFS. So you would have these big files that would contain, all the data that the crawler has crawled from just about any web page the crawler visited. And then you have MapReduce running on top of that to do the processing. And then the output of that MapReduce job, you can consider that output as going into a table like this on Bigtable. Okay, so here you have 2 column families. Okay, the first column family contains the data of a web page, like all the HTML code of a web page. The second column family, anchor, contains all the anchors in that web page. What is an anchor? So every time you have a link that you can click on a web page, that is called an anchor. The anchor, every anchor has at least 2 components, right? It might have more components. There's 2 components we care about here. First is the text that the user sees on the screen, those blue letters that you click on. And the second part is the address to which that anchor takes you. So what is the target of the link, right? So this column family now is the anchor column family. And you have here columns whose names are the target of the link. And the data you're storing there is the text that appears on the web page. Okay. And the row key to all of these is the address of the web page whose content appears here. But this address is in reverse FQDN format, in reverse fully qualified domain name format. Okay. This might sound a bit magical. Okay, but let's see why this design is so. Okay. Right. Why do we need these guys to be in reverse order? Like com CNN www instead of www.cnn.com. Any ideas why this is a good design? It may be recognized automatically as a URL. Someone says no, not really, because the URL would be probably the other way around. Oh, you say it? Okay, I see. That's not the reason. No, it's not. There's no fear that some system would read www.cnn.com and would say that's a URL. That's not the reason why. It's more along the lines of how you design. Remember, as users of the system, we can define what the row keys would be, what the column names, column qualifiers would be. And in doing so, we, in essence, give hints to the system. We affect how these things are sorted and stored. Okay, so think of, remember that the data here is sorted lexicographically by the row key. Okay, so by having the row key be in this reverse sort of format, everything that is under cnn.com would appear close to each other. So if I had www.cnn.com and mail.cnn.com and just cnn.com and news.cnn.com, right? By having com.cnn.whatever be the key, that means that all the com.cnn.whatevers would be, all of these rows would be stored next to each other, possibly even in the same region, if that's where the horizontal cut happens. If on the other hand, I had it the other way around, like www.cnn.com, I would have all the wwws.whatever be together, and then the mail.cnn.whatever be together, and the news.whatever be together. So the data for a single website would be all over the place in my index. Okay, that's the reason why this is reversed. And then what we do with this, you may imagine why we want the link in the anchor and the text in the value here based on what you were doing in your assessed exercise. You know, you didn't really play around with Bigtable or HBase or any of these in the assessed exercise. It was just not enough time for you to learn all of these systems. But think of what the inverse index looks like, and this scheme should not be too foreign, like too exotic. Okay. Okay. Now, one thing to notice here is that this schema, there's actually no schema here. The only schema that is imposed is that you have these two column families. And from that point onwards, you can go and just add columns to these column families by inserting a quadruple with a new column name, right? In a relational database of your, you would need to do a schema update, okay? And a schema update is one of those online DDL operations that are typically fairly, or can be fairly expensive. And you could typically can only do them in one direction. So it's easy to add stuff to your schema, but if you want to remove stuff from your schema, that can get tricky, because what happens with rows that exist already in your database that have that extra data, and so on. Okay. Here you just go and insert a quadruple with a new anchor, sorry, a new column name under this column family, and voila, you have a new column now. Okay. Okay. So back to this breakdown of HBase. So now we know that the conceptual table is broken down into horizontal cuts that are the regions, and this is the unit of replication and load balancing and so on. So if I have a region here with values 1 to 99, another region with values 99 to 199 and so on, if I wanted to create a copy of any of the rows in here, I would copy this whole region around. Okay. And then what happens is that, remember, these regions are further split vertically for column families. So if I have these two column families, data for one column family would be stored in a different place to data for the other column family. So on HDFS, column family 1 would be under, let's call it column family X, under an HBase directory for that column family. And same for a different column family. This would be in separate directories, but as you will see here, if you notice the scheme of naming these directories, the full name is actually /HBase, because that's the HBase data, / name of the table, / name of the region, / column family. Okay, so now there's no way two regions can step on each other's toes, because their data would be stored in separate directories on HDFS. There's no chance that column families would step on each other's toes, because their data are stored in separate directories on HDFS. An extra bonus of this structure is that now I can do I can tweak individual column families differently, because their data is stored in different directories and actually in different files. So I could have a column family that, it's, let's say, amenable to compression. I can instruct HBase or Bigtable to store that in a compressed format. And I could have another column family that is not that amenable to compression, and I can store that uncompressed. Right. And this is one of the many things I can do that can be different across column families. Earlier, we were talking about, for example, Bloom filters. So, Bloom filter is this probabilistic data structure that allows you to do set queries. But what you put in that set, you have options for that. You can choose. So you could insert into your Bloom filters the row keys. And that would allow you to see whether a complete row, whether a row has any of its cells in one of these files, spill files. Or you could insert in that per spill file Bloom filter the row and the column qualifier. And that would allow you to check whether any specific column for that row appears in any of these files. Okay, and you can do one column family in one way and another column family in another way, depending on what are the queries you typically run on those column families. Okay. And again, typically you would split this thing vertically if the operational characteristics of the data in these groups of columns are different. So if we go back to this example here, what do you want to do with the stuff that's in contents? You just want to have the data in there, and you want the data to be stored. You won't have, you won't have up to 3 versions of the data, but that's just the HTML page that you then want to go and read. So this is a long sequence of strings. I mean, this is a long string, essentially, the HTML page. As a string, it's a very good target for compressing. So you would probably store this compressed to save on space. But then once you go through the content of a web page and you process it and you extract the anchors and you store the anchors here, typically the anchor text is very short. This wouldn't be a good idea to compress it, or at least not blindly compress it. But then you typically would access these the cells in these column families in a different way to what you would access them in this column family. For contents, you would probably just scan through the whole thing, extract the anchors, store them here. For the anchors, you would typically treat these as a graph, right? So you would typically want to go here, see what the anchor is. So you say, here I have an anchor, I have a pointer, an edge from www.cnn.com to cnnsi.com. And from here, I can then go and find the row for cnnsi.com and so on. So in this case, the way you crunch this data would be completely different to the way you crunch this data. And that's why it makes sense to separate them in different column families. Okay, so just to wrap up on the data model, typically you can insert stuff, and when you insert, you need to define the row key, the column key or column name, at the timestamp and the value. And when you pull data out of HBase, you can either get a complete row or a specific cell with a specific timestamp, or maybe a specific cell. And if you don't define a timestamp, you will get all the versions of that cell. There is also this very interesting optimization that is what we call a multi-get here, which is if you know beforehand that you want to access a set of rows, you can issue a get for a list of you can group together these gets and issue them as a group. And what happens is that internally the system will look at these gets, look at the individual gets in the list, look at where the data you want for each get resides, and then it would group these gets by region server and send only one request per region server for all the rows that live on that region server. Okay, so a tiny optimization here. And of course, you can do scans, right? And a scan is what it says on the box. It would return all the data between two rows, the row keys. And with scans, you can also have more filters here. You can scan from a start to end row key for specific columns, specific timestamps. You can also add more filters here, like the filters you would have in a SQL query, more or less, only not defined in SQL, of course. There are operational characteristics of how these filters are evaluated that make them not a super good idea. Okay. Typically, you would scan based on just the row keys and maybe column names and timestamps. Extra filters are supported, are not always good ideas. Okay, and then of course you can delete. You can delete a whole row, or a specific version of a row, or a specific version of a column across a whole column family, or a specific version of a single cell, and so on and so forth. Okay. So with these operations here, like the put and the typical gets and the scan, we can do selections. So we can scan over consecutive ranges of keys. We can filter by column name, by timestamp, and we can even I mean, we can project in the sense that we can ask the system to only return data for those specific columns that we want. But how about getting all the values for a column, right? So you see there is no such thing here. There is no get and just a column key, okay? How about order by, or group by, or joins, or transactions, and so on, okay? These are typically not supported by HBase or Bigtable, not inherently by the system. If I want to get all values for a column, what essentially I need to do is to scan through all of the files within a column family and get data for that one column I'm looking for. Okay, there's no way I can limit the number of data I want to scan through, because if I scan with a start and end row key, remember how the data is organized? I would only be reading the files on HDFS that are that have data in between those two row keys. But if I want data for a column, I have to scan the whole thing. Okay. Order by, again, it's not supported. I mean, if the data is ordered somehow, and we know how the data is ordered, right? It's ordered by row key first, then by column key, then by timestamp. If I want a different ordering, what I need to do essentially is I need to change the row keys or the column names. Okay, so essentially I would create a copy, a complete copy of my database, of my table, just to change the order. And doing an order by in RAM may not be practical if my table is too large. Okay. Group by and joins, we can do them just like we would do them with MapReduce and Spark. Same thing apply here. So you can see right away that typically you don't want to be doing group buys and joins unless there's nothing else you can do. It's much more preferable to go for denormalized representation, and having multiple copies of the same thing across rows and columns, than to normalize and then having to do joins. And for transactions, we said early on today that single row transactions are supported. Multi-row transactions are definitely not supported by any of these, like HBase or Bigtable or Cassandra that we will see, or DynamoDB. Multi-row transactions came to the scene of these systems much later, and to this day, I mean, typically this is how you would probably discern between a NoSQL and a new SQL store, right? The ability to do multi-row transactions. And this is everything pulled together. You have your clients. The client wants to first, let's say the client wants to read all the data for a row key. Okay. So what the client does first is it goes to the Zookeeper or to Chubby. It gets the location of the row it's looking for, and that location is in essence what region, what horizontal cat is my row in, and what are the region server, which is the region server that serves that region right now. Okay, the data in there is also read by the master. We'll get to that in a minute. So the client now just reads from Zookeeper the location, it gets an address of a region server, and then asks the region server for that row. And what the region server does is it has this instance of an LSM implemented. So it will take that row, it will go through the in-memory buffers to see whether there is any data for that row in the in-memory buffers. It will look at its block cache to see whether there is any data there. And if the query cannot be answered with just the data that's in memory, it will then need to go and scan the spill files, right? And the spill files for the region server are just pointers to files on its DFS. So it would need to go through the HDFS name node, get the location of block replicas for the file, then go to data nodes and read the data from there. So it would be acting as a HDFS client from that point onwards. Okay. And if the request was a write, then that request would go to the memstore first, append it to the write-ahead log, sync to HDFS, then acknowledge the client. And when that memstore fills up, it would be spilled on disk. So there would be a new file created on some node, or some nodes, I should say, on some data nodes on HDFS to store that spill file. Okay. So a few words about Zabi and Zookeeper, and I think we can wrap this up now. So we said earlier that Zabi is this distributed service, can be used for logging services. It can also be used to store key global data, things such as the column families within every table, what the tablet servers are, like addresses and so on, a mapping of regions to region servers or tablet to tablet servers. It can also be used for access control, and it is typically also used to store the bootstrap information, things such as we said, what are the addresses of the tablet server, and a couple more things that we should see shortly. But Zookeeper or Zabi is also used by the master to detect new tablet servers and to deal with faulty tablet servers. Okay. Typically, this is a highly available service. You would have, I mean, the paper talks about 5 replicas. Typically, you want to have an odd number of servers, and the reason for that is you want to run a quorum protocol with them. So think of it like voting. Okay, so you want an odd number so that you don't find yourself in situations where you have the exact same vote for 2 options. So you have this majority vote. Whenever a majority of your servers is up, then and they can communicate with each other, then the system is go. And when the remaining servers eventually return to the system, they would be updated by whichever servers were live at the point. Typically, this is a master worker architecture. No, that's incorrect. The write protocol is a master follower write protocol. Okay, so whenever you want to write something to Zookeeper or Zabi, you talk to the one node that at that point is the master of the ensemble. That master can change over time, right? So if the master gets overloaded or slow or fails or whatever, the remaining servers will vote to choose a new master. So it's not like you always have the same master, but all the writes need to go through whichever the master is at that point. Okay, and then that master will coordinate with the remaining servers, called the followers in this case, to replicate the change, to replicate the state. In the big table case for Zabi, the algorithm used for this quorum for the state replication was Paxos, and as I said earlier, for Zookeeper, the algorithm is, or the protocol is Zab. It doesn't really matter. I will add pointers to these protocols on the Moodle page in the extra reading section, but these are somewhat outside the scope of this course. So I'll just mention here for those that are interested in these kind of distributed systems. Okay, so that's a good question. So we said here that if we have a read, we will check the mem store, we will check the cache. And someone asked, shouldn't it then go and check the Bloom filters? Yeah, so what I said is, we will check the mem store in the cache. And if it doesn't have enough information in those two places to answer, excuse me, to answer the query, it will then need to go to the files. And when it goes to the files, it will have to go through the Bloom filters. Yeah, good point. Okay. So what now do these guys do for Bigtable and HBase? So the master is responsible for creating regions, or deleting the regions, or merging two regions. So it's the one node that has a sort of global view, and it can decide when two regions need to be merged because they don't have enough data, or when a region, when the user requests for some values to be deleted, and so now a region is empty and it can be deleted, or a new region needs to be created. And it's responsible for assigning tablets to tablet servers, or regions to region servers, and for load balancing among them. It does schema management, but it's not part of the data flow. Okay, it's just like the name node and the job tracker and the resource manager and so on. The other thing this guy does is it detects new or expired tablet servers. So a tablet server that hasn't responded in some time is expired. A tablet server that just appeared out of the blue, maybe failed in the pass and return, or maybe was added to the system right now, is a new one. So the master needs to detect that somehow, and then add that tablet server to the mix. And by adding to the mix, I mean, it would take some regions from other region servers and migrate them to this region server for load balancing and other regions. And what the tablet servers do is that they store and manage the tablets. They serve requests to read and write, that's just last we saw. And they are responsible for splitting the tablets as they grow. So remember what these tablets are? These are these horizontal cuts. Typically, you don't want these cuts to grow too big. So you start with a region being defined as everything that has a row key between 0 and 100, let's say. And then you go and add data to that region. But the more data you add, the more the files of that region grow and grow and grow. You don't want them to grow too large, because then you might have trouble during compaction. So when a region grows above some threshold, the region server will decide to further split it horizontally. Okay, do another horizontal cut, and then you have two regions. One of those regions would stay with the server. The other region would probably be migrated to another region server. But the reason why the tablet server split is that the tablet servers know what is the size of the region in like bytes. The master doesn't know that. The master doesn't know that because that would mean extra load for the master. Okay. Whereas the master knows when where a tablet lives, so they can delete it. It can decide which of these servers is the least, or yes, the least loaded, so to host a new one. And it can know when adjacent horizontal cuts, adjacent regions become too small, so they can be merged. Okay. Okay. So how are these tablets located? There is this sort of inode-like data structure, just like we saw with like HDFS. So you have Chubby pointing, so you store in Chubby a pointer to where something called the root tablet lives. And this is just a tablet like any other. So there is a tablet server or a region server serving this region. And this is a region, this is like a tablet, like a table that has pointers to a metadata table made up of tablets. And these tablets have pointers to the actual regions of the tables of the user. So there's this three-level hierarchy, very, very reminiscent of an inode from those of you who have taken operating systems courses in the past. We can reason about the size of these things, but the important thing here is to keep in mind is that actually all of this is also described in the paper, so there's nothing new on these slides, right? what we can reason about here is that with like 128 megabytes, which is a fairly small amount of data, you can map 2 to the 34 tablets. Okay, so this hierarchy and this structure allows us to pretty much be able to store all of these, to cache all of this in memory, so that walking through this can be very quick, and the extra overhead is fairly small. Okay, and I think that we'll stop here, and these two slides, we will cover them at the beginning of the next lecture. They just describe how tablets are located and how we identify servers that are new or failed. Let's do that next time. Okay. If you have any questions about the content so far, please just post them on the forum. And see you next week. Remember, next week there will be new pre-session reading material and a new quiz, and that will be the last quiz of the semester. Okay. Good. Thank you very much. Have a nice day, and see you in a week.